We often want neural networks to be bigger with more parameters to learn more. But bigger usually means much slower and more expensive computation.
Right. A larger model feels like it needs more computation for every single prediction, which quickly becomes impractical.
This paper tackles that, hinting at the possibility of outrageously large neural networks that are still efficient.
The authors open by stating a fundamental challenge. The capacity of a neural network to absorb information is limited by its number of parameters.
That seems obvious. More parameters mean more knowledge it can store, but also more to process.
Exactly. This limitation became a bottleneck for truly massive models, driving the search for solutions.
The theoretical answer was something called conditional computation. It's the idea that different parts of the network activate depending on the input.
So not every neuron or layer processes every piece of information? That sounds efficient, but how do you decide?
Precisely. This dynamic activation is key to breaking the direct link between capacity and compute.
We discussed conditional computation in TCM 063001. Is MOE a specific way of achieving that?
Exactly. It achieves dramatically increasing model capacity without a proportional increase in computation, using specialized parts only when necessary.
This paper's core contribution is what they call a sparsely gated mixture of experts layer, MOE. This layer replaces a standard feed-forward component.
So it's not a whole new network, it's a specific type of layer within a larger neural network architecture?
Yes, a plug-and-play component that fundamentally changes the scaling properties of the model it's part of.
Inside this MOE layer are thousands of feed-forward subnetworks. Each of these subnetworks is known as an expert.
Thousands of experts? Is each one trying to learn something specific, like an expert in a particular domain?
That's the intuition. They specialize. You don't use all of them for every input.
The paper describes how a trainable gating network determines a sparse combination of these experts to use for each example. This network typically takes the token embedding, applies a linear transformation, and then uses a softmax to get initial expert scores. This is the routing.
Trainable implies it learns which experts to pick, not hand-coded?
Exactly. This learning happens during backpropagation, where the gating network adjusts its weights based on which experts proved most useful for particular inputs, guided by the overall loss function.
Imagine a smart assistant routing your questions to specialist doctors. That's our gating network and experts.
So the gating network is the assistant, experts are specialists. This allows huge model scale?
Yes, only a fraction of those billions of parameters are active per input. The analogy breaks. The assistant also learns.
The initial applications were language modeling and machine translation, fields where model capacity is critical for absorbing the vast quantities of knowledge.
That makes perfect sense. These tasks benefit hugely from more knowledge.
Exactly. It enabled unprecedented model scales, becoming a foundational component for many of the large language models we see today.
So the core idea is conditional computation via a sparsely gated layer. But I still need to grasp how this gating network really works to pick experts.
That's our next step. We'll dive into the intuition behind how these experts operate and how the system decides who gets to work. Let's build a clearer picture of what is a mixture of experts. Imagine you have a team of highly specialized doctors.
So one for hearts, one for bones, and so on?
Exactly. Each expert doctor is really good at diagnosing a specific problem. However, unlike real doctors who might consult or debate, these neural network experts process their input independently, and their outputs are then combined mathematically, not through discussion.
In a neural network, MOE layers are used instead of dense feed-forward network, FFN, layers. These FFNs store model knowledge.
So instead of one general FFN, you have many smaller, specialized FFNs.
Yes, each of those is an expert, and you don't use all of them all the time. How do we choose the expert? We need a gate network or router that determines which tokens are sent to which expert.
So the router examines the token and decides which specialist is best?
Yes, making a real-time dynamic decision for every piece of information flowing. For example, the token more is sent to the second expert. Each token gets unique processing.
So if I input a sentence, each word independently goes to specific experts?
Yes, each token's path is unique, determined by the router, leading to conditional computation. This router is composed of learned parameters and is pre-trained at the same time as the rest of the network.
So the router isn't hand-coded, it learns to route effectively through training. That's a key advantage for adaptability.
Exactly. It's an adaptive learning component that evolves to route tokens optimally.
I assumed a token would only go to one expert, but it says we can send a token to more than one expert? Why?
Sending it to just one might be too restrictive. Allowing two experts provides a richer processing path.
So like getting a second opinion or combining expertise?
The core concept isn't new. The roots of MOEs come from the 1991 paper, Adaptive Mixture of Local Experts.
So an old idea, but only recently practical for large neural networks?
Yes. Advances in computing and training methods made sparse gating possible at scale, especially for transformers.
This blog reminds us that in traditional networks, process all input data through every layer. MOEs fundamentally change this.
And that's where the efficiency comes from, right? Not doing all the work all the time.
Yes, by intelligently deciding which parts to activate, MOEs pick capacity benefits without proportional compute cost.
This sounds too good. Any downsides? Batch sizes in MOEs are effectively reduced as data flows through the active experts.
It's a challenge. If 5 tokens go to one expert and others scatter, some get full batches, others get tiny ones.
So experts are overworked or underutilized, a bottleneck.
Despite these challenges, MOEs offer a powerful advantage in pre-training. While they allow for massive parameter counts, they also mean a MOE model should achieve the same quality as its dense counterpart much faster during pre-training.
So it's not just about bigger models, but also about getting the same performance with less time or compute in the initial training phase? That's a huge efficiency gain.
Exactly. This means you can either train much larger models for the same compute budget, or you can reach a target performance level more quickly, translating directly to reduced flops for comparable quality during pre-training. It's a key part of their appeal. This brings us to a key problem, ensuring experts are used efficiently. It's called load balancing.
So, how do they solve that? And how does this lead to concrete model gains?
We'll look at mechanisms addressing these challenges, and then see a famous example in action. To address expert selection, Shazir's work introduced noisy top K gating.
Top K implies it selects a fixed number of the best experts, like 2 doctors for a patient?
Exactly. Instead of picking the single strongest, it selects the top K experts, typically 1 or 2.
Let's break down the noisy top K gating mechanism. First, the gating network computes scores for each expert. Then, we add a tunable random noise to these scores. This slightly perturbed score vector is then used to select the top K experts, meaning we zero out the scores for all other experts. Finally, we apply a softmax function to the selected K scores, which gives us the weights for combining the outputs of those chosen experts.
Noise? Why add randomness when picking the best experts?
It helps prevent the router from always choosing the same few experts, encouraging exploration during training and contributing to better load balancing across experts.
So the noise helps explore, but what prevents the network from just converging back to popular experts once training stabilizes?
That's where a critical component comes in, an auxiliary loss function. This loss penalizes uneven expert usage, encouraging the gating network to distribute tokens more equally among experts during training. Without it, some experts might starve, while others get overloaded.
Once the top K experts are chosen and their weights determined by the softmax, what happens next? Each chosen expert processes the input token independently, executing their specialized computations.
So they all work in parallel, and then their individual results are somehow put back together? Is it just a simple average?
Not simply an average, but a weighted sum. The article explains their outputs are multiplied by the weights given by the gating network softmax. So if an expert had a higher weight, its contribution is more significant. This final combined weighted output is what passes on to the next layer in the transformer stack, completing the MOE layer's operation for that token.
These mechanisms for expert selection and load balancing were crucial for scaling MOEs. They allowed for the development of models like Google's switch transformers, which used 1.6 trillion parameters.
1.6 trillion. That's a huge leap in scale. What's an example of a more recent open source model using this architecture?
A prominent example is Mixtral 8x7b. It's a large language model from Mistral AI, which achieved significant performance with a relatively small active parameter count by leveraging the MOE architecture effectively.
So MOEs use a trainable gating network to dynamically route tokens to a sparse combination of specialized experts, allowing for massive model capacity without proportional computational cost. And they employ noisy top K gating with auxiliary loss for efficient load balancing. That's a lot of clever engineering.
Exactly. And this innovative architecture has truly redefined what's possible in large-scale neural networks, making previously outrageously large models a practical reality.